This is 4I, exercise 4I, volume of prisms and cylinders. All right. All right, you're right. We're ready? Yes. I know that's been wet since art. But we're now in mathematics. Giving you that time, can we focus? Okay. All right, thank you, team. So, volume of prisms and cylinders. What I want to go through today is a revision of what we did in 4H. So exercise 4H, I first introduced you to volumes, and that was in Go6 when we did it. I want to remember, if you wrote your notes, how do you find the volume again? I gave you a formula in general. What is the volume formula again?
For what?
That's very good. So that's what I mean. So it doesn't have to be to a particular shape, but just in general for prisms overall, doesn't have to be a rectangular prism, could be a triangular prism. I gave you a general formula. Okay, so you started off with 4H, you had a rectangular prism, and I asked you, what is the formula for the volume of a rectangular prism? And you said?
Height times width times base.
Very good. So it's normally length times width times height. And I said that volumes are three-dimensional shapes, which is why you have 3 dimensions there. You've got a length by width, and then you've got a height. But then I gave you a second rule. And I said, this is actually volume is equal to, and anyone have that rule? Yes, Michael.
That was.
Because that's what we're going to carry on today.
Capacity is volume of fluid or gas that a container.
Good, just under that. So under the definition of capacity versus volume, I mentioned about volume formula. You had length times width times height, and I also had equals something. Has anyone got it? Because if you haven't got it, then I want you to copy this one down then, okay? I want you to copy this one down. This is A times height, H for height. Now, what is A? Area. So, the way I tried to explain in that session exercise 4H is that to find a volume, often, for a prism anyway, it is the area. So notice length times width. You learnt that in area. Length times width is the area of what shape again?
2D.
2D, okay? And specifically the first rule that you learnt was a rectangle, right? What they're trying to say here is if I drew a rectangle like this, and I found the area, that's a 2D, that's a flat 2-dimensional shape. So this table here, if I wanted to paint this tabletop, this is the area. I'd go and buy paint and I work out the area. So it'll be length by width, right? But if I want to change this into a volume, it now becomes a 3D shape. So this is flat, that's 2D. When I make it 3D, so say I've got this now box, right? And I want to know how much water I can fill into this box here, or this container. It is length by width again, but then there's a third dimension, and it's the height. Can you see this third dimension allows you to tell how much of those areas can you fill based on that height. That's why it's length by width, because it's the area of the surface that you're looking for, and how far down in that third dimension. That's what this rule is telling you, because when you add in that third dimension, which I'm going to do now, when you add a third dimension to all of it, you now get a rectangular prism. That's all it is. So, how does this relate to all the things that you've done so far? You've learnt different shapes. You've learnt area of a circle. So this is 2D. What's the formula for area of a circle again?
Area of a circle was pi times d. An angle out of 360.
Very good. Radius squared. And yes, angle out of 360. That's even better. Okay, so that gives me a circle. That's 2D. But if I make this 3D now, I would add in a third dimension to it. And you can see if I pull this down and I add a third dimension to it, what shape am I getting now? What shape do we call that?
A cylinder.
A cylinder. So then when we ask, what is the volume of a cylinder? All you're doing is find the cross-sectional area or the area of the flat surface you're looking for, and then add a third dimension to it. That's why you're multiplying to the height. So what they're trying to show you here, you can find the volume of all these three shapes simply following the idea that you just need a surface area and that third dimension that you're extending. See, that is an area of a trapezium. So the 2D is a trapezium. If you extend it by that third dimension, you get the volume of a trapezium or a trapezoid. If you then have a look at this one, this is a triangle on the base. That's an area, that's 2D. But if you add in that third dimension, if you multiply that, what you're now finding is the volume of a triangular prism. Okay, so each one, they all follow this concept that you're finding the surface area 2D and then you're extending it in the third dimension. That means I can make up a shape. I can do this. I can do that. That's a shape, right? You can find, let's say I told you the area was 3 squared meters. That's just area. But if I want to make a volume out of this, okay, so if I want to make a volume, I'm extending this, and what you'll get is this shape. Can you picture that? This is now 3D, it's like a sponge, right? The volume of that sponge is based on what is the area times the third dimension. This is my height. This is the rule in general for any prisms. Area times height is how you find the volume. But you didn't learn that when you were in primary school because there would be too much to explain at that point. So all they taught you was the volume of a rectangular prism. Ooh, wow, that was loud. Volume of a rectangular prism. They didn't explain to you why it was width by length by height. Okay, because all you're really doing there is you're finding the area of a rectangle and then you're multiplying by that third dimension in the height. Okay, and so that's why when I often ask students, what is the volume? Most students will know or remember from primary school that the volume in general is length times width times height. That's what most students will remember. But then from there onwards, if I teach about the volume of a cylinder, volume of a triangular prism, volume of a trapezium that's in 3D, a lot of students can't do that. They can do this because you've been drilled by that. You've been drilled and learned how to do this type of question in primary school. But what I'm trying to teach you now is to understand, actually, you can apply that concept into multiple shapes as long as you know the area of the cross-sectional area, and you multiply it by the third dimension, you should be able to find the volume of 3D shapes. Okay, but in this particular question, we're working with prisms. Okay, so let's have a look at some of the shapes they've given you here. Okay, so that you can see the pattern. So remember, the formula that I want you to get used to is volume equals to area, so the cross-sectional area multiplied to the height. So let's have a look at this shape here. See that shape? It's not a rectangular prism, and neither is a triangular prism because they're making up a shape for you. What they're trying to tell you here is that this cross-sectional area, see that? That's 2D. That's a 2D shape. They've already told you that the area is 10 squared centimeters. If you want to make this into a 3D shape, you just need to know what is that third dimension, what's the height. You should be able to find volume because volume is area times height. Now, do I have the height? Do I know that third dimension? What's the length of that third dimension? 3. So if I were to answer this question, the volume of this shape, how much can this container contain in terms of liquid? It should be area, which is 10, times the height, which is 3. This gives me, yes, you're correct, 30. What's my units? Not squared? Cubed. So this is called cubic centimeters. So you would say I've got 30 cubic centimeters to imply that this is a volume and this is a 3D shape. Okay? On the top here, this is area, made sense why it was squared. So 10 squared centimeters, right? So that's how you would do this type of problem. And all you're doing in each exercise is they're trying to get you to visualize, where is that area. Now, your job is to find that cross-sectional area. Now, what do I mean by cross-sectional? Wherever you cut on this shape, we call it a cross-section when it is consistent. That shape is the same from the start to the end. So, for example, imagine this is a block of cheese. If I cut it horizontally, okay, if I cut it like this, across, and I'm going to get you to use your imagination right now. If I cut it like this, okay, so I cut it right across horizontally. Just imagine if I'm just cutting it across like that. And I lifted this shape up and I pulled this apart. What do you see as the bottom shape and on the top shape? Can anyone picture that? Trapezium. Very good. You get a trapezium on the bottom and you get a triangle on the top. Can you guys picture that? So I'm going to draw it again. This is the triangle. And then here, because I've chopped it off, this should be the bottom, right? Now, these two shapes are not consistent, especially if you look on the bottom here. Every time I chop it, the shape is different. The size of the trapezium and the size of the triangle is different. But, listening, thank you, eyes and ears towards me. When we're talking about cross-section, what I wanted you to see was the area was different, right? But which way can I cut this if it was a block of cheese that the area is always going to be the same? You see, if I cut it this way, if I cut it down and I separated it, what shape would you see now? A triangle. And what's interesting here is no matter where you cut it, just like when you cut the block of cheese, the triangle is always the same size and the same shape as the front. Okay, this is called a cross section. So with all of these shapes, all of these prisms, have a think, they all have a cross section. See this one, I would be cutting it sideways because on the bottom, this shape will give me a triangle that's exactly the same as the top. Think about cylinders. Where I would cut it is if I cut it horizontally, the shape would be a circle and it's still the same as the top. If you have a look at this shape here, same thing. Where would I cut it? If I cut it down, you see, I would still get the same shape. From here, from the front and the back, they're all the same. These are called cross-sectional areas. The reason why you need to know what a cross-sectional area is that out of all these volumes, when you're finding V equals area times height, that A is a cross-sectional area. You can't just find any random area. It has to be area that is consistent throughout each and every one of them. Now, the first few questions, they try to help you by highlighting which areas you need to find. Later on, when you do these questions, they're not going to tell you. So you don't know which is the cross-sectional area. You have to picture, where is my cross-sectional area? If you go through the next shapes, these are all cylinders now. And if you go further down, they won't give you the shapes, and you have to picture what the shapes are. So you can see the skills is simply volume equals area times height. Your job is to find the area, the cross-sectional area. Okay, now this ties back all the way back to, and if you've forgotten all the formulas, remember we have a page where we did revision. The page is called revision, and if you click on it, we already had the formulas here for you. So this has the formulas that we were working on. So please go back to that and refer to those notes to help you answer those questions there. Okay? So today's lesson, it is going back to volume, but this time I'm just adding on the idea. It doesn't have to be a rectangular prism. You can have a pentagon and make it a volume. You can have a circle and make it a volume. You can have a triangle and make it a volume. So your job is to be able to use your calculator and identify where is the cross-sectional area and multiply it by the height. Okay, so you can do that with anything. Say if I drew a letter T for tran, so you can find the area of that composite shape. But if I made this a 3D shape, I would have to extend it by this third dimension, and suddenly it now becomes 3D. Okay, so this must be my height, and then this is my 2D area that you'd have to work out. Okay, that's the cross-sectional area. So if you can try to picture that, it's always A is the cross-sectional area, height is that length that you're repeatedly extending in the third dimension. That's the idea. So if anything I wanted you to take out of this lesson was to understand what I meant by cross-sectional and what the height is. Okay, anything that you make 3D that is a prism often has to have a cross-sectional area and you extend it. Even this room right now that we're in, technically the carpet is the cross-sectional area, and then you multiply it by the height. So the shape on the top and the shape on the bottom should be the same. So if you look on the floor, the shape of the bottom floor and the shape of that top has to be exactly the same as what it is on the bottom. This is a prism. So this volume of this place is easy if we know what the area is, multiplied by the height, we know how much this room can contain. Okay? So I'm going to stop there. That's my video for today. But that's where we're at. Now, I know some of you might still be on 4H. 4H, this is 4I. If you can work on 4I, it's the same thing as working on 4H. Start on 4I. You can skip 4H if you haven't done that. I know. I know. Well, you've done more work, though. So that means it's good for you. Second part is, can you please check on Teams 4I, check the assignments tonight. Let me know, give me some feedback on how that goes. Okay? Who said?
When will we give a 4H?